Hello, my name is Mike Smithson, and I'm from the Australian National University, and I'm going to be talking about the receiver operating characteristic area under the curve, or mean ridit, as an effect size measure. Several authors have recommended adopting the ROC area under the curve, or AUC, or mean ridit, as an effect size because it's an important and interpretable type of effect that conventional effect sizes don't measure. It's base rate insensitive, robust to outliers, and it's invariant under order-preserving transformations of the dependent variable. A lot of researchers have rediscovered and oftentimes renamed the Wilcoxon test, Mann-Whitney U statistic, AUC, and/or ridits going back to the 1940s. And several researchers have recommended the AUC or mean ridit as an effect size, but suggested applications for the AUC and mean ridit have been limited to group comparisons, and usually just to two groups. Also, ridits are treated as if they're applicable only to ordinal variables. None of these restrictions are valid. To find out why, let's have a look at the AUC for two-group comparisons and see why limiting it to two-group comparisons makes no sense. A typical ROC curve graph looks like this: the false positive rate on the horizontal axis, the true positive rate on the vertical axis, and the area under the curve then is referred to as the sensitivity, usually the medical test that's being evaluated. This isn't very helpful, but if we actually think about what's being plotted, then it's two cumulative distribution functions, or CDFs, of a non-disease sample versus a disease sample. And the area under the curve is the probability that the CDF for the disease sample is greater than the CDF for the non-disease sample at any threshold t on the dependent variable scale. As several authors have observed, these could be CDFs for any two groups. So we get a group 1, group 2. Group 2 might be no treatment, group 1 might be treatment, for example, and the AUC now is in the role of an effect size with a probabilistic interpretation. Namely, the probability that a randomly chosen case from group 1 scores higher on y than a randomly chosen case from group 2. This is a clinically meaningful effect size measure. If group 1 is treatment and group 2 is no treatment, then we're talking about the probability that somebody randomly assigned to the treatment group is going to score better on y than somebody randomly assigned to the no treatment group. What no one seems to have realized is that these could be the CDFs for any two conditional distributions. So they could be conditioned on any two values of continuous predictor x, for instance. We could have a CDF of y if x is x1, and CDF of y if x is x2. x2 could be the mean of x, for instance, and x1 could be one standard deviation above the mean. So we could have the AUC now as the probability that a randomly chosen case where x equals x1 scores higher on y than a randomly chosen case where x equals x2. So the AUC can be applied to any model that predicts conditional distribution parameters, and the predictors can be categorical or they can be quantitative or continuous. Let's start with a simple example, linear regression. If we allow the normal assumptions for linear regression, then there is a normal approximation relationship between Cohen's d and the AUC. Given a regression coefficient bx and standard error of the estimate SE, we can get a Cohen's d by taking bx and dividing it by the standard error of the estimate, so the AUC becomes an effect size for this coefficient. And also, corresponding to the benchmark Cohen's d's of 0.2, 0.5, and 0.8 for small, medium, and large effects, we get the AUC benchmarks, 0.56, 0.64, and 0.71 for positive d's, and for negative d's, we just subtract each of those from 1. So we can apply the AUC and ridit potentially to any GLM with a continuous predictor. So given a continuous predictor x, let's say whose mean is mu x, we consider the CDF biplot that has the probability that our h of y, where h is the length function, is less than the threshold, given that x equals mu x plus 1, against the same conditional CDF where x is mu x. And so, as a consequence of that, the AUC for the CDF biplot is the probability that a randomly chosen case from the distribution of hy, conditional on a unit increase in x, will score higher than a randomly chosen case from the distribution of hy with no increase in x. Well, what about ridits? Ridits originated as a scoring method for ordinal variables. The definition of a ridit for the jth category in an ordinal random variable scale is the cumulative distribution up to j plus the PDF, or probability density function, at j, p of y equals j, divided by 2. Now, the reason we're dividing by 2 is because we're assuming that if, let's say, group 1 and group 2 are tied at j, then for the underlying continuous latent variable, the true scores of group 1 will be higher than those of group 2 half the time, and vice versa. So we're dividing by 2. We can also rewrite the ridit in this more conventional form here. Okay, so the mean ridit, R, for y2 relative to y1, is the sum of the probabilities for each of the categories for y2, which I'm calling gamma j's, multiplied by the ridits taken from y1. And they can be interpreted as the probability that an observation randomly sampled from y2 will score higher than an observation randomly sampled from y1. The mean ridit, R, approaches the AUC in the limit as the scale becomes more fine-grained, so as the number of bins in CDFs approaches infinity. The mean ridit, therefore, can be applied as an effect size measure for any discrete quantitative or ordinal variable, and in particular, it can be applied to ordinal logistic regression models. So let's see how that can be done. And before we get on to that, let me just briefly talk about why we would want to do it. As you would know, the typical effect size measure for an ordinal logistic regression is a cumulative odds ratio. These are notoriously difficult to interpret. What I'm going to be offering here in the form of ridits is an easily interpretable effect size measure as an alternative. So let's say we've got a binary predictor, parental education, predicting an ordinal rating by secondary school students of whether they're unlikely, somewhat likely, or very likely to apply to university. So we've got parents without university education and parents with university education. Those are our two groups that we're using to predict this. Let's suppose we've run our ordinal logistic regression, and we've got a significant coefficient. It's positive. It's 1.127. Ordinarily, we would go on then to talk about cumulative odds ratio. We would exponentiate the coefficient, change the sign, and so on and so forth. What I'm going to do instead is to use this model to construct the estimated CDFs, and then from that, the ridits, the mean ridit. So we use the parents with no university education as our referent distribution. And in that case, the estimated CDF just uses the intercepts, or the cut points. And so we find that the predicted probability that students will respond unlikely is 0.59, and the predicted probability that they'll respond either unlikely or somewhat likely is 0.92. Now from this, we can compute the ridits using the formulas that were on a previous slide. I won't go into that in any detail. Instead, I'm just going to go on to look at the subsample with parents who have a university education and have a look at their CDF. Okay, now we have to bring the coefficient into play, and doing that, we find that the probability that students will respond with unlikely is 0.32 instead of 0.59. And the probability that they'll respond either unlikely or somewhat likely is 0.79 instead of 0.92. Now, plugging those results into our CDF and getting the PDF from them, and then using the ridits that have already been obtained from the previous slide, multiplying the PDF by the ridits gives us the ridit scores, and if we add those up, we get the mean ridit, which is 0.652. So in other words, kids whose parents had a university education have a probability of 0.652 of giving a higher rating on how likely they are to apply to university than kids whose parents didn't have a university education. That's the effect size that this model is providing for us. And I'm claiming that this is a lot easier to interpret than a cumulative odds ratio. Okay, well, let's consider the scope of applications here. The mean ridit for, or AUC, is an effect size applicable to GLMs for any ordinal, interval level, or ratio level dependent variable. That dependent variable can be discrete or it can be continuous when it's interval or ratio level. It can be applied to GLMs with continuous and or categorical predictors. The demonstrations in the paper that is the companion for this not only include linear regression and ordinal logistic regression, but I've also supplied demonstrations in gamma regression, log normal regression, and beta regression. It measures an easily interpretable kind of effect that isn't captured by conventional effect sizes. It's more widely applicable than Cohen's D or Pearson's R. In particular, we could certainly apply it to meta-analysis. Grissom in 1994 recommends that, for example. And therefore, it merits much more widespread usage than it already has received so far.